everybody to come here. That is the TYPT round 2. So at first, I would like to introduce the viewers. I am J.S. Tsai from National TY101 University.
John Liu from National Tonghua University. Zhong Zhang from National Chengdu Education University.
From National Taiwan University.
Okay. So for the leader, please introduce your team members.
My name is Huang Dongqi, and my team is You Can See Me. This is Wu Bingchen, this is Zhang Zhenmin, this is Watson, and this is Yang Jiachen.
Okay, so I'm for the team activity, and my name is Lin Yongzhang. And as for my members, here is Luo Dazhao, Chen Guoyu, Wang Ruichen, and Zheng Di.
I'm the captain from Team Excelsior, and I'm Chen Yuchen. She is Lin Yichen, he is Lin Kaiwen. He is Hou Shenzhao, he is Deng Yuchen. Thank you.
So for the opponent, please ask the challenge.
We would like to challenge problem 14, ruler trick.
Problem 14. Ruler trick.
Yesterday we just reported, so I don't think that is acceptable.
So please read select. Over there.
Sorry, we would like to challenge problem 4.
Problem 4. Shooting rubber band. Okay, so that's it.
Yes.
That's it. So please write down the name of the reporter, the name of the opponent, and the reviewer.
everyone. My name is reporter, and there are power questions for program, and I'm Johnson. And this is my test. If I remember distance, nano on current strength, drop, and PV is 5, and automatic distance, then rubber is 5 bridge. And below is my main box. The 1 is the rubber band rotation, and the 2 is the rubber band tensor axis, and 3 is the lunch elevation angle. And this is my another observation, and you can see a video one. This is this moment, and you can see it has the update and just tired. Yeah. And this is another on the jet, and you can see it's now. And you can see it's very perfect, and because it's stretched and not leak. So yeah. And so I will define the potential axis. And you can look at the red picture, and this pen I define this is the vertical axis, and in the right picture, and this is the pen is the horizontal axis. And this is the mouse pad, and when the rubber band fly will rotate, and you can see the upside the rubber band rotate, and the direction is forward, and the airflow is backward, so we will cause the air velocity go slow, and you will cause the high pressure, and this push the mountain force and push the rolling down. And this is the original parameter is this, and it's the LD, and you will equal to the temperature, and temperature just the short side I call was 1, and the long side is the n, and it's just the ratio, and you when you stretch you just like the refrigerator 3, and the front is the short side and long side, the spring constant, and the deformation amount. So I derived the list, and so I got this answer into just like this square, and just like n minus 1 and plus the 1 over n, and times the 1/2 k and L0 squared. And I make this slicer, and this means when the n is more and more big, and you can see I can get this just like n minus 1. You will more and more just like is elasticity plus potential energy will big, and so it can be shot to reach the more distance. And I think the mountain sport in fact vertical is just like this, and the elastic potential energy will equal to k potential kinetic energy plus the moving kinetic energy. And so just like this picture, I did it only cost the rubber band go left and right, and so it will moving with the vertical, and so you will not, I think you will not affect this distance more. And my control variable is the launch initial height and rubber band quality and total stretch long. This is the jet, the two sides. Okay. And independent variables is the jet ratio and stretching method and rotation, this is direction and launch elevation angle. And this stretching method is the vertical axis and horizontal axis. And this framework is just like independent variables. Okay. And this is my experience setup, and I just put the rubber band in a stick, and this picture two is my launch base, and you can see the up one is the elevation launch base, and you can see this vertical stick. I start the small block on it and measure the degree on it, so you can do every angle you want. Yeah, it's very simple. So the up one is the vertical axis. So and just like and yes, it's same. Yeah. Okay. So I drew my experiment one stretching rubber band. So this means with the short side and long side ratio will equal to one ratio n. When the n is more bigger, the elastic energy will bigger too. But this I make this experiment is not we can do the extra experiment caused by the elastic battery. So yes, just very simple experiment too. Okay. And now I will define the rotate. Just like the direction, the finger rotate with the fist. And this picture. This is the four finger direction. Just I define, and this is the forward direction, and so this I define is counter rotate, just like this, and this is the rotate. So I will use the last paper. So to my experience too, just the rotation axis, and you can see this is vertical axis, and just like this red, and it's between the along and counter rotate, and I find this picture the counter rotation with a horizontal axis is too close, so I want to find why. I think the reason why is the distance. It will equal to the horizontal velocity times the flight time and flight. So we can see that when the rubber band rotate with counter rotate, and the magnetic force will push in this direction, and you will cause the up force and the back force. So the up force will affect the time, but I think the gravity will far greater than the up force, so it will be very small, and the back force will cause the velocity very cause the velocity horizontal velocity down. So I think you will like this, and this is the best angle of the oblique moment, and I derived this and got this answer. So I just like when the object with the oblique moment the 45 angle will reach the best distance, and I just this my experience here with the different rotate. I just want to know if the counter rotate and the rotate is relation. So it's because this degree, 0 degree and 40 degrees is very So and you can see the rotate is always farther than the counter rotate. Okay, and so this is my experience for. And with a different elevation angle. And the next picture is my the first. I take the 10, 20, 30, and 40 degrees to do my experiment. And you can see when the elevation angle is the 20 and the 30 degrees, you will further than the 10 and 40. And I take the 3 degree around the 20 and 30, just like 14, 25 and 35, and I do the second experiment, and I got the data of the 25 degrees will the virus. And while the elevation angle around the 25 degrees well has the farthest distance, and I think was by the initial range term. And it means this is the stick, and when you rotate with a long rotate, and the upside, this is high tension. So it will when you reach the top of the stick, and the downside was hidden. So and the last moment, the upside force will face down, and the short side will follow. So you will cause the rotate. And just like this picture, and if we cause the forward velocity, it will cause the distance more high. And so this is the resistance force direction. And this my conclusion. Rubber bands, if rubber band long side is more bigger, and with horizontal axis and a long rotate, everything go around the 25 degrees, the rubber band will have the farthest distance. And it's my look forward and different parameter of the rubber band, and 2 is the more accurate elevation angle, and 3 is the rotational behavior in the rubber band life.
Okay.
Oh, it's my presentation.
Warren, please.
Okay, so I would like to ask you a few questions. So, does a rubber band slide faster with speed?
That's the problem. It's the process of the
Yeah, but does it fly faster?
right base.
Its velocity. Is it?
I didn't consider that. I just consider it rotate.
Okay, thank you. Is the spin speed same every time when you stretch the rubber band? It's not uniform.
I really must not do this, and so I can make sure, because I take the data as I do a very small experiment, and I take the average data.
Okay, thank you. Does the elastic constant of your rubber band stay the same?
Yes,
Yeah. Like when you stretch it, does the elastic constant of the rubber band stay the same with every elongation?
yes. This is my control variable, and every rubber band is the same curve.
Okay. Will the elastic constant be different after you shut the rubber band?
I think not.
Okay. How do you measure the length of the rubber band?
Yeah.
Like you said the circumference, right?
I use a ruler, and lower in there, I just take a bar, S5.
Yeah, I mean the total circumference of
Have
the
stress.
No, the whole rubber band. Okay, thank you. Did you control the initial shooting angle of it?
Time is up.
statement. A rubber band may fly a longer distance if it is non-uniformly straight shot, giving it a spin. Optimize the distance that a rubber band with spin can reach. I'll be mainly focusing on the parameters that affect rubber band flight distance and why do rubber bands fly farther with spin. So this is the outline for the recorder. He used Magnus force effect to explain the curve of his theory of his rubber band and also the vertical axis of his the spin. And also he used some formulas to explain the proportion between the long and short sides of the rubber. And also his experiments consist of stretch ratio, the stretch method, and also the rotation axis direction, also the launch elevation angle. However, he did not have any error analysis. And here are the strong and weak points. So he explained the phenomenon well, and also he has a clear illustration of the experimental setup. And he compared his experimental data with his theory. Also, he considered the Magnus effect. However, you can't release the rubber band stable with its setup. And also, he didn't talk about the measurement of angular velocity. And he didn't explain the difference between uniform and non-uniform straight wave. And also, he didn't demonstrate the theory well. And he didn't consider air resistance. And he lacked of explanation about its deviation. And here are my points to be discussed. So first, in the theory, I would like to talk about the elastic constants of the rubber band, also the rotational inertia of the rubber band, which is about its speed and its mass, which will affect its flight distance very essentially. And also the non-uniformly stretched length, how to define it and other factors. And then I'm going to talk about the energy. This is the potential energy of the rubber band. And also I'm going to talk about the force, the friction, and also the air resistance, which I think is a very important part during this experiment. And about the setup, I'm going to talk about the stretch length. Also, I'm going to discuss about the initial angle of the shot, and about the experiments, which is the comparison between uniform and non-uniformly stretched rubber bands, the measurement, and also the parameters, which are the initial angles and the boundaries of this experiment, and the deviation, which is the interference between the rubber bands and the setup. Also, the difference in elasticity of rubber band, and also elastic fatigue, which is what might happen if you shoot a rubber band too many times, which will cause the experiments to have some deviations. Also, the stability of shot distance. Also, I would like to add that I would like to talk about the rotation speed, also, and how it affects the flight distance. Thank you. So I would like to start first by asking that every rubber band is slightly different from each other. So how do we solve the problem of different rubber bands having different elastic force?
I take the average of I do this one experiment. I take the more rubber band and do the very more data, and I take the one rubber band data average and the all rubber band average, and I make the total figure, so I can make sure it is. So I data. Yeah.
So you mean that you conduct the experiment many times and you take the average of the rubber bands?
Because
The shot distance.
my every experiment is take the different rubber band, and so I take a very small rubber band. So this is the average.
Yeah. So if you do the average, then how do you know which rubber bands you need to take into account? Like which of the data you need to take into account of your data?
And because it's I take the sandbag just to take just buy it from the store and it's sandbag. So I just take the cover and I think you will.
Okay, yeah, I see what you mean. But what I think is that if you buy some rubber bands at the store, every rubber band would be a little different, and some will have a very big difference because every rubber band is slightly different. They have different elastic force. So what I think you should do is get a dynamometer to measure the elastic force every time you do the experiment.
And before I do the experiment, I take I just test the rubber band quality and I just value and it's
Okay. So can you please turn to a page where you will set up? So did you do the experiments with angle?
yeah
Different. Yeah. So the elevation height. So you vary the elevation height. Also you vary the initial angle. So you have two variables. So how can you analyze the data if you have two variables?
no I put this stick this from this to this, so I can make sure the buttons is like this there, it will offset. But I can show the elevation angle. I just control it.
Okay, I see what you mean. But I think that if you change two variables at once, it will cause the analysis to be wrong. Because what I think you should do is you should just change the angle, but however you should control the initial height of the shot of the rubber band. Okay. I would like to ask that does the elastic constant of your rubber band stay the same? Which I asked in the short question. So can you briefly explain how the elastic constant stay the same? Like when you stretch it to 15 centimeters or 20 centimeters, does the elastic constant stay the same?
When I measure this, I just take the low ratio of the 1 and n. So I can just like my experiment one is the ratio of this. So I said it's very simple experiment. So
Okay. Can you explain the relation between the force and the elongation? Can you please come to the whiteboard? So this is the F and this is the X, which is the elongation. So can you draw the graph, which is the force related to the elongation?
this distance
Yeah.
force is the jet.
Yeah. No. The force, the elastic force.
Yes, elastic force is outside and the downside is plus. It's total.
Yeah. It's force.
Because it's ratio when n is more big, it's elastic force just like my just like I derived this lecture just like n and this was n minus 1 and plus the 1 over n. And I got a lecture is it will more and more big just like this and normal. It's just like when there is 1 and 2, you will big and very, very small and will just like.
I would like to address my question. Okay, so it's like, do you think Cookstyle is available? I mean, do you think Cookstyle works in this function, like in the force of the rubber?
I think it's not the false law. So because the Fuchs law is just like Fuchs law is the this is perfect this, but
Oh, you're talking about the potential energy, right?
no. The rubber band's elastic constant is just like this and just like this. You know, in this area, it's just.
Okay, please, thank you. What I think is that the rubber band's constant is shaped more like an S. It's force.
Yes,
It's like this, right?
yeah, this
So-
is the elastic fatigue. Yeah.
Okay. Okay. I would like to ask that since are the spinning speeds same when you do the rubber bands non-uniformly? Like when the rubber bands are non-uniformly stretched, does the spin speed are the spin speeds same every time?
You said the vertical axis.
The vertical? Yeah.
I do the
Is the spin speed the same?
yes.
If you non-uniformly stretch it to the same thing.
Please, can you repeat?
Is the spin speed same when you stretch the rubber bands non-uniformly every time?
I think it was not because when the rubber is fly, his kinetic of the rotate will
Okay, thank you. But the opponent disagrees with the report because I think that if the elastic force is the same, if you non-uniformly stretch it to the same length, then it will cause the rotation speed to be same every time. Okay. So I would like to ask that which direction does the rubber band spin if you non-uniformly stretch it? So here is the rubber band. So if this part, if you stretch it, this part, this F is larger, then which way does the rubber band spin? Does this, which way does it?
vertical axis.
Yeah, where does it spin? Which direction does it spin?
I think your if the forward dash is this, if I want to make the rubber bands rotate.
No, which way does it spin? Does it spin clockwise or counterclockwise?
Okay. The opponent, please summarize the discussion.
It is my summarization of the discussion. So the non-uniformly stretched rubber band gives it a spin, which stabilizes the flying motion, and then the friction between the cell and the rubber band will affect the velocity, and the air resistance decreases the flying distance and the size of the rubber band. The boundaries in these experiments are elastic fatigue. And then the graph of the elongation of force exerted on it seems like S shape. Okay, thank you.
Okay, so I'm the reviewer for team activity, and I'm gonna ask a question for both the reporter and opponent. So, what do you think is the most important parameter? The launch angle the spin or the elongation? The most important parameter.
I think it's the average angle, and because the rotate,
I think it's a launch angle. Launch angle.
yeah.
Okay. And
I think it's the elongation of the rubber band because it's directly closely related to the elastic force which rotates the rubber band.
okay.
It's shot.
And I'm gonna ask the reporter, how did you know the distance? Did you consider the first bounce or after it bounces? When you first touch, because when you shoot it, it might bounce a few times.
No, I just take this landing moment.
And how do you know the landing moment's distance between the launch?
I just take I just take slow motion, and
Okay, thank you. Do you think the air resistance will have a big effect on the results?
I think it's not. Yeah, because if it's uniformly straight, I think it will not. But I do it where it has the differential.
Okay, thank you. And what is the point think?
I think the air resistance plays a very important role in this experiment because the rubber band is too light to have a small inertia and the air resistance as well. Thank you.
Okay, I wanted to ask the opponent, what do you think you can use Hooke's law when you analyze the stretch of the rubber band? Okay, and does the reverse think you can use Hooke's law on the, as it like imagine it as a spring?
I think yeah.
Okay, do you think the best launch angle for the rubber band changes with initial height?
Right.
Yes, because when you shoot it from table, does the best launch angle, is it 45 also?
Yeah.
And what does the opponent think?
You mean
Does the launch angle varies from different initial heights?
yeah, because it's you mean his setup or
Or I'm just thinking the launch angle?
the launch angle affects the launch distance.
Hi, I'm the reviewer for team relativity, and here's a common statement. So a rubber band might fly longest distance if non-uniformly stretched, and then when you give it a spin, and the reporter should optimize the distance with the rubber band that the spin will change. And in this theory, we talk about elastic constant and the rotation of this rubber band and how the energy transfer, and we talk about its vertical and different rotation axis and how the magnets effect will result on the effect on the results. And instead of using different rubber bands and a launcher he made himself, and it has a high-speed camera. And in his parameters, he has changed spin and no spin, and then talk about the short side and long side straight ratio and a different launch angle. And in the reporter, I think he has a fair quantitative phenomenon explanation, and he has a well-modeled rubber band launch, and he has a clear observation video for us to look at. But I think he lacked simple explanation for the phenomenon, and then he didn't consider air resistant, and the theory and experience doesn't really match, and it's not clear on this equation in theory. And one, I think he has a good and clear remark and a fair amount of key questions, but I think he didn't let the reporter understand all of this question, and he has not good understanding on the problem. And the missed point is about, I think they should discuss about some of the air resistance and how the area measure the distance properly, because I think there will be some hard deviations, and how the spin effect on the distance, and that's the most important part on the problem statement, but I think the reporter should do more on that. And here's the discussion part. So the point asked, do you think the elastic constant will be the same? And the reporter said yes, and I think there sometimes is the fatigue, and it will not stay the same. And then point asked the elastic constant on the rubber band, and the reporter said he uses average data, and I think it's a good way to fit. And then opponent said, will the angle affect the length of the on the setup? And the reporter said it won't change, but I agree with the opponent that the setup will be changed, because if it changes the angle, the distance will be changed also in his setup. And then the opponent said, can you use hook saw? And the reporter said no. And I think it's in some conditions it's possible to use hook saw, because in some part when you stretch it, it will have it's proportional to its elongation. And then the opponent asked, when it's not uniform stretch, the rubber band will have the same speed. And then the reporter said the kinetic energy will change. But I think when you stretch the rubber band uniformly, there will be more potential energy inside the rubber band will make it fly faster. And I asked both opponent what's the most important parameters, and the opponent thinks it's elongation, but I think it's spin, because spinning it will make it more potential in the rubber band, and it's also stated in the problem statement. And I asked the reporter, how do you measure the distance? And he said he'd take it in slow motion and look at his first landing spot, but I think it might not be accurate. Maybe you could dip the rubber band in some ink and then see what's marked on the floor. And then I asked, will the air resistance affect? And of course it won't affect much. And I agree with the reporter, but the air resistance is proportional to the area of the rubber band. But the area is very small in rubber band, so it could be, you don't need to consider it that much. And the point then is very important, and it's proportional to the area, but it's very small, so I think it's not that important. And I asked them, can you use hook saw to explain? And of course said no, and I think in some conditions, maybe like some elongation part is still possible to use. And that's my presentation. Thank you.
Very good. So the conclusion remark of the reporter.
And I think the Hooker loss and it can be considered in my theory some part, and it's not all the same, all the match in the rubber band elasticity constant. And next, I want to correct my answer. And I think the most important variable is strut length ratio, and second is the average angle. And reviewer asked me how did I measure the distance with the landing resistance moment, and because I can make sure the accurate his landing, so I take the very large data to average this, so I can make sure this very yes, just like my data. Yes. Okay.
The touch time for the viewer.
So, I have a question. First, to reporter, your theory says that the longest distance will happen at 45 degrees, and you observe it 25 degrees, right?
Yeah.
Do you have an explanation? Why is 25 less than 45?
Because in the initial, I think we are around 30 degrees, but I do my experience 25 degrees, so I think we are the one of the reason I think is the lentil, and because we are in a case elasticity penetration, we are equal to this. We are test, and it will cause the resultant force direction will be a little down change. So I think we'll low, it may be low the 30 degrees a little.
What comment do you have the explanation why he observed 25?
Because at 45 degrees, the rubber band, when the rubber band shot, the air resistance will be too big to affect its flight distance. So if you change it to be like a little horizontal to the ground, and you will
I think the launch angle should depend on the initial height. So when it's shot, if it's in a shot in a high place or shot on the ground, it will have different launch angle. And I think the reporter should do some experiment to tell us about that.
Any very simple reason for what caused the spin? Which is really okay. Very simple.
I think just like I just said, this lunch talk, initial talk, because
When you spin it, you will have more potential in the rubber band cell.
if you now your rubber is straight, you will have a spin, and you will have more rotation.
So, question to the reporter. So, how you, since you mentioned this quality of the rubber band, how you, because it's available, how you do that, or how you control it?
Because I can control very accurate, so I take the average of the every railway. And
Can you explain it?
So you can, how you quantify
You have to measure every elastic force which the rubber band contains. Like when it's stretched to a segment, it has to have the same elastic force.
I think if you use Hooke's law to explain this, but when you use Hooke's law, the rubber band may not be proportional when its elongation is in its length. So if you do an experiment, there will be some part of it will be proportional, which is when, so there will be some part you can use Hooke's law to explain it and do the calculation.
Is there any further questions? No? Then let's make the score. 7, 7. The score for the opponent. 7, 9, 7, 7, 8. The score for the reviewer. 8, 9, 8, 9, 8.